Hello, everybody. Thank you for joining me today. My name is Anthony LeBoy, and I am here to talk to you about the science behind LASIK. So, what's on the agenda today? The first is going to be what is LASIK? We're going to go through a brief history of it, what it is, how it came to be, and what it is today. And then we're going to go on into the optics of it, what the physics of light are in the natural world, and how light moves through a material. Then we're going to pivot into the cornea. We're going to talk about the anatomy and physiology of the cornea, everything that goes into it, and how light passes through that to get to the retina. And then we're going to briefly touch on wavelengths and radiation, the electromagnetic spectrum, and then we're going to end off on the lasers, the big important part of LASIK. So first, LASIK. It is laser-assisted in situ keratomyolysis. Uh, we're going to talk a little bit more about what that means in a second. And so the history of LASIK. Back in 1948, Dr. Jose Barraquer Moner develops the first instance of keratomyolysis. And if we break that word down, we have kerato pertaining to the cornea, which is that clear dome structure on the front of the eye. And then mylusis is the carving or shaping of something. So this here is the shaping of the cornea. And so the way that Dr. Monet did it back in 1948 is he got a volunteer patient. He surgically removed the cornea off of that person's eye, and he froze it in liquid nitrogen, and he put it on a miniature lathe, a lot like this little lathe that I've got here. And then he basically just carved, he smoothed out the curvature of that cornea. And in theory, what he wanted to do was to smoothen out the curvature of it so that light would bend a little differently through it. And that way, the patient would no longer need glasses. Their vision would be corrected to 20/20. That was the thought behind it. And you're probably thinking, that's pretty barbaric to cut off the front of someone's eye and carve it down on a lathe. But it actually worked pretty well. After this, the patient saw pretty well. There were very minimal complications from it. And so that ended up paving the way for a whole myriad of different refractive eye surgeries after that. And so in the 1960s, a little bit about the laser, they started development on the first excimer laser. And in 1971, Nikolai Bazov demonstrates the first operational excimer laser. And so pretty soon after that, people started thinking maybe we can use this laser to operate on tissue, to ablate tissue, because when it was first developed, really the only people using it were computer companies, namely IBM. They were mostly using it for creating, etching, and laser engraving their computer chips. And so after that, people started thinking that maybe we could use this on human tissue for surgeries. And so a couple of years later, with the help of some other doctors, 1988, Dr. Golem A. Payman performs the first laser-assisted in situ keratomyolysis. And so this laser-assisted part, we're using lasers, obviously, so that's pretty evident. The keratomyolysis, we talked about that. It's the carving or the shaping of the cornea. This in situ part right here, in situ means on site or in its original location. When Dr. Monet did it in 1948, it was not in situ. He ended up surgically removing the cornea off of the patient's eye, carving it down, and then putting it back on. Here, with the laser, we are doing it while the cornea is on the person's eye. And so a little bit about the optics and the physics of light. Light is all around us, and it will do one of three things, or a combination of the three. It will reflect, diffract, and refract. And so reflection, everyone knows reflection when you look into a mirror. It's when light reflects or bounces off of an object entirely. And so this little diagram here, we've got a mirror at the bottom here and this little ray of light coming into it. Uh, this ray of light will hit it at an angle of incidence, is what we call it, this angle right here, and it will bounce off completely into another angle, which is this angle right here, the angle of reflection. On a flat mirror, this angle of incidence is actually going to equal this angle of reflection, and so it will reflect at an even uh, angle there. And so next, we've got diffraction. Diffraction is when light is dispersed and is bent around an object due to the waves of light trying to escape. And so a good diagram that I've got here is with an aperture, like an aperture of a camera, where the waves of light are trying to fit through this little aperture, this little hole here. And the only way to do that is to bend around it or bend through it. And so you get left with these distorted waves of light. And so a more evident, a better example of this would be with clouds. When you look at the clouds and you see the sun behind the clouds, you see the light sort of diffuse behind the cloud, and around it sort of scatters in different directions. That's what happens when you see diffraction. And so lastly, and most importantly to the presentation, we're going to be talking about refraction. Refraction is when light is bent due to its wavelength and the difference of speed from one medium to another. And I've got a better photo here, a better diagram of it. And so what happens in refraction is when a ray of light hits another medium, this little block here, instead of going all the way through it, just like it would in air, it is bent. It's bent down a little bit before it exits at another angle. And that is because of the index of refraction of that second medium. The index of refraction is a measurement of the difference of speed of light through air versus the speed of light through another medium. And so when light travels through a material, it will slow down. That the waves of light, the particles, will slow down when it hits this second medium here. And so the way we calculate for that is through Snell's law, where we have N1 is the index of refraction of the first medium. Most of the time when we do this formula, it is through air, and so the index of refraction of air is 1. Sine theta 1, that is the angle of incidence right here. That's the angle that it hits that second medium, equals N2, which is that second medium right here, sine theta 2, which is the angle of refraction here. And so a good example of refraction that you'll see if you don't wear glasses would be something like this, where the pencil is in a glass of water. And so the index of refraction of this water is different than the index of refraction of air. And so light travels at a different rate. And because of that, the image shifts a little bit to the left. It jumps a little bit. And so instead of the pencil going straight through like that, you see it move a little bit to the left there. And so next, we're going to talk about diopters and prisms. What is dioptric power? A diopter is a measurement, it's a magnitude of the strength of a lens. It's a measurement of the lens's focal length. And what is the focal length? The focal length is the distance that light travels to converge onto a point, which is the focal point. And with this being physics, there's obviously going to be a formula involved. And so the optical power formula is the one that we use, where P is the dioptric strength, the number in diopters, equals 1 over F, where F is that focal length. And so very similarly, prisms are going to operate with dioptric power. Prism is a material that reflects, diffracts, and refracts light. And so by that definition, lenses are prisms. In a prism, light is bent toward the base of a prism. And so here I've got a better drawing of it that I made. And so right here we have an example of a negative diopter lens with a lens, a very simplistic view of it. Basically what it is two prisms on top of each other. Where with a negative diopter lens, we have two prisms on top of each other where the apex of the prisms touch. And then positive diopter lenses are a little different. With a negative diopter lens, this is more so what it looks like in real life, a concave lens. What it does is light through the center of that lens will pass straight on through, but the more we decenter the ray of light onto that lens, the more it's going to bend toward the base of that lens. And so with a negative lens, light is going to be diverged instead of converged. And so the reason it's a negative lens is because the focal length, the focal point, is going to be behind the lens instead of in front of the lens. And so the way that we calculate for this is we basically just trace back this angle here onto a certain point, which is going to be the focal point here. And the focal length is right behind it. And that's how we get the calculation for the focal length of it. And so same thing with a positive diopter lens. You see over here a more real world application of it is a convex lens like this, where light is converged after it passes through that lens. And so just like with the negative lens, the optical center, it passes straight on through, but the more we decenter it, the more it's going to bend toward the base of that lens until it hits that focal point. And then the focal length is in front of the lens, so it's going to be a positive diopter lens. And so we use these lenses for different things. A positive diopter lens we would use for hyperopia, which is farsightedness. Uh, with hyperopia, the issue is that the focal point, the image is not focused onto the retina. It's focused a little bit behind the retina. And so this lens in front of the eye, what we do is we converge it at a different angle than what the eye would converge it. And so that pushes that focal length a little bit more forward. And so we've got the cornea now. There's a whole lot that goes into the cornea, and so we're going to simplify it a little bit. The cornea is responsible for about 69% of the total refractive power of the eye. There are two lenses in the eye, or two natural lenses, I should say, in the eye. And the first one is going to be that cornea. It's that clear dome structure that we're going to talk about. That's where the LASIK surgery will take place. And then the second lens is that crystalline lens inside of the eye. The crystalline lens is responsible for the other 31% of refraction in the eye. And so we're not going to talk about the crystalline lens here. We're just going to focus on the cornea here. On average, it is 43 diopters of power, which is a very large amount of power. And it's only half a millimeter thick on average. And so it's pretty impressive that the human body can fit 43 diopters into half a millimeter lens. And so it consists of 5 separate layers. From anterior to posterior, we've got the epithelium, we've got Bowman's layer, the stroma, Descemet's membrane, and the endothelium. And for the purposes of LASIK, we're really only going to be talking about the stroma here. And so to talk about the stroma, we're going to talk about what refraction through the cornea is. And so I've got photos here. Emetropia, most people know it as 20/20 vision, perfect vision. What we want to happen is light converges onto a point right here, right on the retina. That's where you get the best focus for that light. And so in myopia, for example, nearsightedness, what happens is that focal point, this right here, falls just short of the retina, and so that image is not completely in focus. And so with glasses or contacts, the way we correct for this is with a negative lens. We will diverge the light a little bit so that pushes back that focal point a little bit more. And that way it's in focus right on the retina. But with LASIK surgery, what we're going to do is we are going to remove tissue. We're going to ablate some tissue to change the curvature of that cornea, so that way, without the need of glasses, we diverge the light a little bit, and so naturally you get that focal point back onto the retina. And so some more about the stroma. The stroma is responsible for 90% of the corneal thickness. That's where we are going to ablate tissue for LASIK. And a better image of the layers of the cornea are right here. This is the stroma, that third layer. It's the thickest layer, and it's responsible for most of the cornea's refractional capability. And so when light travels through the cornea, when it hits the stroma, it's going to bend the most, is basically what it is. And so because of that, in LASIK, we are going to temporarily remove the first 2 layers, the epithelium and Bowman's layer, and we're going to use that laser to take away parts to carve out and shape a new curvature into the stroma. And so before we get into the lasers a bit more, we're going to talk about wavelengths and the electromagnetic spectrum very briefly. Uh, in the electromagnetic spectrum, what happens when we decrease frequency, we are also increasing the wavelength. And inversely, if we decrease the wavelength, we're also increasing the frequency here. And here's an image of what the waves do as we do that. So when we go up in wavelength, we decrease that frequency, it gets lower. But if we go up in frequency, the wavelength shortens. From wave to wave, it's going to be a smaller wavelength. And so for the purposes of this right here, we're only going to really be talking about ultraviolet right here, the visible light spectrum, and infrared, this little part right here in the middle. And so UV and infrared, UV light ranges between 100 nanometers and 400 nanometers. The smaller the wavelength, the higher the frequency. And so with UV, it's going to be a smaller wavelength and a higher frequency than infrared light. Excimer lasers, the big important laser that we use in LASIK, will operate through UV wavelengths. And so infrared ranges from 780 nanometers to 1 millimeter, which is quite a bit larger than the UV wavelength range. And so we divide infrared light into 3 segments. Near IR will be from 780 nanometers to 1.4 micrometers. Mid IR will be 1.4 micrometers to 3 micrometers, and far IR will be 3 micrometers to 1 millimeter. And so here's a better diagram of what we're going to be talking about with the wavelengths, where ultraviolet is going to be this little section right here. The infrared is this big section right over here. And then the visible light spectrum, where we can visually see these wavelengths, is right here in the middle. It bridges between UV and infrared here. And finally, we are going to talk about lasers. There are 2 types of lasers that are commonly used in LASIK surgery. We've got the excimer lasers that we briefly talked about, and femtosecond lasers. And so we're also going to talk about their uses in refractive eye surgery here. The excimer lasers, there are a family of lasers that operate in the UV spectrum. More specifically, they're going to operate between 157 nanometers and 351 nanometers. They use a mixture of gases that are excited by electrical pulses. With the LASIK laser, the specific gas that they use is the argon fluoride gas. And so how this works is electrical pulses are put into the cavity where the gas is stored, and electrons in the gases jump to a higher energy level and come back down at a lower energy level in the form of UV light. Specifically, it's going to be at 193 nanometers. That's the wavelength that we use to ablate tissue in LASIK surgery. And so the frequency and precision of UV wavelengths allows for ablation at a molecular level. And so instead of burning the tissue around it, it's going to be very precise with where it hits. And so it's going to ablate the tissue that we don't want, the unnecessary tissue, with very minimal thermal damage to the surrounding tissue. And so since we are using high energy photons, this type of ablation is known as photoablation. Next, we've got the femtosecond lasers. With the femtosecond lasers, they are a family of lasers that operate in the infrared spectrum. Specifically, these lasers are going to be in the near IR range. It's going to be anywhere from 800 nanometers to 1,560 nanometers. And they operate by a series of short pulses of energy at 1 femtosecond each, hence the name, which is 10 to the negative 15ths of a second. And so they are used to create the incision on the cornea to access the stroma. And so more on the femtosecond laser. Before the femtosecond laser, there was the microkeratome. Not many practices use the microkeratome, if any at all, really. It has increased risks of rippling, and healing is not the same with that rather than the femtosecond laser. But what they did before the conception of that laser was this microkeratome. It's basically just a blade on a track. And so they put that track on the eye where they want it, and that blade will slide forward and take off the top 2 layers here of the cornea, so that we have access to the stroma, and that way the excimer laser will do its trick. The femtosecond laser, after its conception, most practices started using that instead because it allows for a much higher precision and accuracy, and it's far lower risk than that blade was. And so the way that the femtosecond laser works is it will basically dissect the cornea from within. It will create a pocket between the stroma and the other layers, and that way it creates the incision there where we can access the stroma and ablate the tissue with the other laser. And so the excimer laser, what it does is ablates and removes corneal tissue from the stroma. It works in coordination with other measurement interfaces and the other laser to ensure accuracy. There's a whole lot of measuring involved in this to ensure that there is the most accuracy and precision at work so that we don't take off too much, we don't take off too little. We are right in the pocket of 20/20 vision there, and it allows for the patient to have little to no refractive error by creating a new curvature. That laser will remove material from the stroma so that light will bend at a different angle, and that way the light will focus right onto the retina. And so here we've got a little diagram of the steps involved. They'll do all the measurements they need to. This is a little topography of the cornea. The femtosecond laser will create that pocket and the incision so that we can remove that flap of those first two layers to access the stroma right here. And then the excimer laser will do its trick. It'll ablate the necessary tissue that it needs to. The flap comes back down. It heals pretty quickly, actually. The cornea heals very quickly, and soon after we are left with 20/20 vision. And so that was it. That was the science behind LASIK. And so in this presentation, we went over the physics of optics, what happens when light travels through a medium, what happens in the natural world when light hits an object. We went over the physics and biology of the cornea, the anatomy physiology of it, how light bends through the cornea to hit the retina, and then the electromagnetic spectrum, how it plays a role in the chemistry and the physics of these lasers, and how engineering and more modern advancements are going to pave the way to a much safer, more accurate laser surgery. And that was it. Thank you so much, everybody. My name is Anthony LeBoy. I would love this presentation to be submitted into the Tennessee Association of Science Department Chairs Conference. And again, thank you very much. Have a good day.